If your AI helper keeps hallucinating functions that don't exist, make it repo-aware. We will index a small code base and pass relevant snippets into the model for better suggestions. You open a project and the assistant invents a helper that is not in the repo. That wastes time and breaks trust. By grounding suggestions in the actual files, you get concrete hints you can verify and test. Today, you will see how to build a tiny repo-aware assistant in Python that finds files, ranks them, and composes a safe suggestion you can check. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Code assistants solve a simple, practical problem. They need to map a question to the right pieces of code. The naive approach is to ask a model without context and hope it knows the repo. That often leads to invented helpers. The repo-aware approach indexes the code, retrieves the most relevant files, and only then asks the model to suggest edits or snippets. Success looks like fewer hallucinations and faster debugging cycles. The intuitive idea is retrieval, then suggestion. First, find candidate files that mention the term. Next, expand those files, score them by how specific they are to the query, and keep a small shortlist. Finally, compose a recommendation that references actual lines and file names. This trades a bit of pre-processing for much safer outputs. We will build a tiny pipeline with 5 focused steps. Each step is compact and maps to a code snippet. The snippets use an in-memory dictionary as our repo, so the logic stays obvious. Now we will scan the repo to count files that mention a search term. This snippet scans a tiny in-memory repo to count files mentioning a query term. We store 3 short files in the dictionary repo and define Q as the search term. A list comprehension checks if the substring Q appears in each file's text. We sort the matching file names into hits to keep results stable and predictable across runs. Finally, we print how many files contain the term, which is a quick latency-free signal of relevance in the codebase. The printed count shows whether the repo has enough surface area for meaningful retrieval. Next, we will build a lightweight index of the repo words. This snippet tokenizes files and builds an inverted index to ground retrieval. The dictionary tokens maps each file name to its lowercase word list, giving us lightweight structure. We collect all unique words into the set vocab, then create inv, a map from word to the file names containing it. The small list Q words holds the unique query words we'll refer to later. This index is a fast, memory-friendly primitive for code search because it narrows lookups to only relevant files. The printed vocabulary size confirms indexing coverage across the repo. Now we will turn those matches into a ranked list using inverse document frequency. This snippet ranks files by inverse document frequency to prefer specific matches. We compute IDF per query word using a simple 1/1 plus document frequency formula based on the inverted index inv. The dictionary SC sums IDF values for words present in each file via tokens, producing a lightweight relevance score. We sort by score descending and then by file name for stable tiebreaks and join names with arrows to show order. This approach is fast, predictable, and avoids overweighting common terms. The printed ranking reveals which files are most likely relevant to the query. Next, we will pick the top candidates to limit context size. This snippet selects the top K files to trim context and latency costs. We keep order as the stable ranking from scores SC, then slice the first K entries and join them into a compact string. K is the retrieval breadth budget. Increasing K pulls more context at higher cost, while decreasing K speeds up downstream steps and reduces token usage. Keeping the shortlist small reduces noise when you later prompt an LLM. The printed top K confirms the final budgeted context set the assistant will rely on. Finally, we will compose a concise suggestion that references actual files and phrases. This snippet composes a tiny grounded suggestion from retrieved code. We choose SRC and DST based on likely reuse, pulling words from repo SRC and extracting a short phrase around the term token. The variable phrase captures a concise, human-readable concept the assistant can recommend. We assemble MSG as a direct, actionable hint referencing exact files, which makes it easy to verify and test. This deterministic template simulates a cost-free baseline before integrating an LLM. The printed suggestion shows a concrete, repo-aware action the assistant proposes. In a real project, this maps cleanly to safety and auditability. The same shortlist and phrase extraction can be fed into a model as context. The model then generates code conditioned on actual files instead of vague memory. That reduces false positives and provides traceable references back to the repository. Recap: what it is: a small retrieval pipeline that finds and ranks files and then composes a grounded suggestion. When to use it: whenever you want an assistant to edit or suggest code inside a private repo or a messy codebase. One caveat: this toy scoring is simple and can miss deeper semantic links that require embeddings or more complex models. Next step: scale the retrieval by swapping the IDF scorer with an embedding index, and tune the shortlist size K to balance latency and accuracy. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.